outside times whole thing equals outside times whole thing. And that idea is presented in class, and when I did that and just said, do this, nobody would get it. So let me show you why it works and put that visual in your head, why it works and why what our brains want to do won't work. And then I'll come right back here and do this problem. So we have a circle, and I've got a couple secants that are coming from one point, which is kind of important. And I can move this around, and I can move these around. And this guy, I can move it, but it is also the one that changes the size of my circle. I'm going to measure all these things and show you what's going on. If I take outside times whole, the blue outside right here on the outside piece here is 7.7, and the whole thing is 14.2. And then the outside on the green is 8.2, and the whole length from here to here is 13.3. Now, you might think I have this set up. I take the outside times the whole thing. 7.7 times 14.2 works out to be 109. 8.2 times 13.3 is 109. What happens if we start moving stuff around? If I change the numbers, that product stays the same. What happens if we make everything really different? What's happening to that product? The lengths are not the same. When you take the outside times the whole thing, stays the same. That's the theorem that works. This is the theorem that doesn't, but it's the one that your brain is going to want to do, and that is inside times outside. This piece times this piece. This piece times this piece. There's another theorem somewhere down the road here where that is the case, but not when this point is on the outside right here. Let's look at the numbers. Again, the actual lengths of inside and outside are going to be different, but when you multiply them together, you also get different answers. So no matter what I do and where I move things around, outside times the whole thing stays the same. Inside times outside is 62. Inside times outside is 36. Now, something else you want to look out for is when you get problems where it's not a secant, but it's a tangent, and that's when this is 1 point. Inside times outside is, this one's cool. Look at that. The inside turned into 0. You know why? There is no inside. I think that's really nifty. Pause this if you need to and slow it down and look at these numbers. I'm going to go back and do the problem now. All right, let's set this up. We now know outside times whole thing is going to equal outside times whole thing. So we're talking about this piece is an outside piece, and this is a whole thing, which means we'll have to add these two together. Outside, whole thing. We're going to have to add those two pieces together to get the whole thing, because this 11 is on the inside. It's not the entire length. It's on the inside. Okay, so to start, we've got the x minus 1, and we have to multiply that times the x minus 1 plus the 1 plus 2x. And that's going to equal the 7 times the 7 plus 11. I know you can do that in your head. I'm just being real clear because I'm teaching. All right, let's simplify and solve this thing. Negative 1 plus 1, yay, they cancel. I love it when that happens. So I have x minus 1 being multiplied times, well, just a 3x, because what you're left with is an x and a 2x. And on this side, it's going to be 7 times 18. All right, so we have x minus 1 times 3x. This is distributive property, but it's going backwards, because x minus 1 should be in parentheses. I just didn't draw them. So I have to take the 3x times the x. That is going to give me 3x squared. And then I have to take the 3x times the negative 1, which is going to give me a negative 3x. And that equals 7 times 18, 126. Subtract the 126 from both sides, and you have a 0 on that side, and now we have a trinomial that you can factor. But the first thing we're going to do is probably take a 3 out. If 126 can be divided by 3, we can make all of this a little simpler. And yep, it's 42. So we have the 3 factored out. Now we need to factor this trinomial, the x squared minus x minus 42. So what we're going to have is 3 times something going on with a 6 and a 7, because that's how you're going to get the 42. There's more than one way to do that, but I know I have to have a -1 in the middle. The 1 is invisible, remember that. So the only two numbers that make a 42 that are 1 apart are 7 and 6. Now it's just a matter of fixing up the signs. Since this needs to be negative, it means the larger number is negative and the smaller number is positive. So the 6 is positive and the 7 is negative. You multiply three things together and they equal 0. That means one of them must be the 0 that zeroes out the whole answer. So it's either 3 equals 0. I know I'm going to cross that off in a second. Don't freak. X plus 6 equals 0 or x minus 7 equals 0. Let's solve these two. Subtract 6 from both sides. I'm going to get x equals -6. Add 7 to both sides. I get x equals +7. Now we put on our common sense hat. 3 doesn't equal 0. And in geometry class, we get negative answers sometimes, but this doesn't make sense as a negative answer because -6, if you put a -6 up here on this outside, that would turn this outside chunk between M and L to a quantity of -7, which doesn't make any sense. So this doesn't work. So 7 must be the one number that we're going to use here. Now, to figure out what K to M is, I mean, after all that work, you want to be done right here and put a box around it, but that's not the answer to the question. You're not wrong. If you stop here, you're just not finished. K to M is the whole length on this side. So we need to find what these pieces actually are. So I'm going to substitute the 7 in here. So 7 minus 1 is 6. And then if I put the 7 in here, I'm going to get 15. The whole length, remember this is the inside part, this 1 plus 2x, the 15 is the inside piece. 15 plus 6 is our answer. So it is Km equals 21. Cool. You like that problem? Watch this video next. I'll see you guys next time. Bye.